Hello guys, welcome back to the channel. Now we will move on with some more quality problems on Coulomb's law. So let's deal with the first question now. Here it says a thin wire ring of radius r has a electric charge q. What will be the tension in the wire if a point charge q naught is placed at its center? Now let's draw the diagram and we will try to understand from this. Here we are given with a wire, thin wire. Let's say this is the wire here, and at the center of it we have a charge. Here it is given at center we have charge q naught, and the wire is given a charge q. Now they are asking what is the tension in the wire, because of this charge, this ring charge will get pushed sideways like this. Considering both are of same nature, both are positive or both are negative, in that case this will be pushed. So in that case the wire will be try to stretch away outward towards outer side, radially outward it will try to stretch, but it is a rigid body, so it won't stretch practically, but there will be a tension developed along the length of the wire, and we need to find that tension. So how to solve it? First of all, I am choosing a very small element from the wire surface, from the length of the wire. Let's say here this is our very small length. Consider the length is actually very small. We are just drawing it big so that it will be easy for us to analyze different parameters, but we are assuming the length to be very small. Here at the two ends I am drawing the tension. Look, here I am drawing the tension like this. Tension will be along the string and away from the body, right? So like this the tension I have drawn. Let's say this angle, each side, this one and this much part, both are considered to be d theta. This side is also d theta. Now in the total ring the charge is capital Q. In, let's say, I have lambda which is defined as Q by 2 pi r. R is the radius. So in that case I need to find what is the charge on this much portion of the length. So the length will be considered as r into the angle, which is 2 times d theta, and the charge, if I write charge dq can be written as lambda into dl, which is lambda into r d theta. This much is the charge. Now we need to solve the problem. Now how do we do it here? See, if we see this much portion of the length, tension is acting along the length, right, like this, right? So if I draw a perpendicular here, this angle is written as d theta, so this angle will also be d theta. So I am drawing on one side only, I am drawing it to show for now. So this side angle is written as d theta. So total, this is tension and this angle is d theta. Here I can write the net force is T sine d theta, but similar force on the two sides, here and here, the net force downward will be 2T sine d theta. So I can write the net force downward here, downward means towards center this way, the net force on the element is 2T sine d theta. But this force, this portion is in equilibrium, right? Because it is not moving. So in that case I can say net force this way must be equal to net force this way, but net force outward here is only electrostatic force. So how do I write the electrostatic force here? The electrostatic force I can say, considering both are assumed to be point charge, because I am assuming this to be a very small length element, so both can be treated as point charges. I can write the net force is k q naught dq by distance between them, which is r, so r square. Now if we write all the forces. No, the second step here, this is 2t. As the angle is very small, instead of sine d theta we can directly write as d theta, that is equals to k into q naught into dq I can write as lambda into r into 2 times d theta. Here by mistake I have written as d theta, so this will be d theta times 2, because this length is r into 2 d theta, so dl will be r into 2 d theta. So that's what we have written here, this much by r square. Now if we see, the 2 term gets cancelled, the d theta term gets cancelled, so I am left with tension T equals to k q naught lambda. Here r and r also gets cancelled, so k q naught lambda by r. Again k value comes to be 1 by 4 pi epsilon naught into q naught. Lambda I can write as q by 2 pi r, and 1 r is already remaining from the previous step, so my tension comes to be q naught by total 8 pi square epsilon naught r square. This comes to be the answer. So this is the answer for this question. Now let's move on to the next question. Here the question says, two small equally charged spheres, each of mass m, are suspended from the same point by a silk thread of length L. Two silk threads are there, both are of each length L, and two masses are hanging from the same point through the two threads. Now the separation between the spheres is x, which is very very small than the length L. It is asking find the rate of charge dq by dt with which the charge leaks off the spheres if their velocity of approach varies as v is alpha by root x form, where alpha is a positive constant and x is varying here. See, as the charge leaks off, both the spheres come closer and their velocity of approach, relative velocity of approach, is given to us. So to solve the problem here, let's first draw the diagram. I am drawing the two threads here. So let's say these are the two threads and the two masses, and here I am drawing the free body diagram of the left one. So it experiences a downward force which is mg. There is a electrostatic force of repulsion because both are of same charge, so they will feel an electrostatic repulsion between them. This electrostatic force for now I am writing as F, and there will be a tension which is along the string here. This way there will be a tension. So I am taking, say, see, I am considering the half angle, the two threads, they make an angle alpha with the vertical. Let's say this angle theta with the vertical. This angle I am taking as theta each. By symmetry, I can say both will be same angle, and I am assuming that angle to be theta. So in that case, this angle will also be theta. So I am considering this angle to be theta as well. So I can see this is tension T, this angle is theta. So this component of tension will be T cos theta, which will balance mg, and this component will be T sin theta, which will balance the electrostatic force F, and that's why the ball will be at that point. So in that case, I'm writing T sin theta equals to F, and T cos theta equals to mg. Now if I divide both of them from these two equations, if I divide them, I get tan theta equals to F by mg. But now see, if I consider this side of the triangle here, it is a right angle triangle, and this length will be x by 2, right? this length will be L, and we are given that this x term is very very small, so x by 2 term obviously will be very very small than L. In that case I can say this angle theta will be very small angle. So for small angle, tan theta can be approximated here as x by 2 by L, or I can say as x by 2L, which is equals to f. The term f I can say as k q square by x square, and I'm multiplying 1 by mg term here, 1 by mg term I'm multiplying. So from this I get the equation. See, all the x term I'm bringing to one side, I get x cube equals 2k q square L by mg. So if I rewrite the term, see x cube here, x cube term, and here there is a q square term, both x and q are varying, but 2k L and mg term are constant. So I can say x cube equals to constant times q square. Now I'm taking differentiation with respect to time on both sides. If I differentiate it, 3x square differentiation gives me, sorry, x cube differentiation gives me 3x square into dx by dt. This equals to constant times q square will be 2q into dq by dt. So see here, this dx by dt, this is the velocity of approach that is given to us. What is velocity of approach? According to the question, it is v equals to alpha by root x. So I am replacing that term here. So I am getting, see, 3x square into alpha by root x equals to 2cq into dq by dt. So again I am rearranging the term. They are asking us to find dq by dt. I am keeping dq by dt on one side and taking this 2cq term to the other side. So I am getting, see, 3 alpha by 2c into x. See, here there is x square term and here a root x term. So this gives me x to the power 3 by 2. So I am getting x to the power 3 by 2 by q. I am rearranging again the term, just mathematically rearranging them so that I can easily get the answer. X to the power 3 by 2 by q, I am squaring both of them. If I square both numerator and denominator, I get x cube by q square. But this does not match the equation, so I am taking again root over of entire term. So squaring and taking root over cancels out, and the term remains same, right? But now here, see in this equation here, x cube equals to c times q square. So x cube by q square equals to a constant c. That c we have already assumed. So let's replace it. We get the term as 3 alpha by 2c into root over of c. So finally we get dq by dt equals to 3 alpha by 2 root c. This gives us answer 3 by 2 alpha into c value. C, I can say, what is the value of c here? The constant is 2k L by mg, right? So here I am getting 1 by root c. The root over of 1 by c I am writing as mg by 2kl. K value is 1 by 4 pi epsilon naught here, and this is our answer here. See, we can get a variety of answer here. In this equation right here, if I replace c here itself as c equals to x cube by q square, if I replace this term here, so in that case here there will be x cube term, x square and x cube will cancel out. There will be a single x term left out here. That x term can go here and gives us x to the power 3 by 2. So even though final answer will look a different way, if we put the values, our final answer will be same. In that case, here in the denominator we will get x to the power 3 by 2. In this kind of arrangement, we are getting x to the power 3 by 2 in the numerator, but alpha by c here. In those kind of arrangement, this alpha by c term will change, but x to the power 3 by 2 will come in the denominator. Final answer will be same. If we are given with the values and we put the values, our final answer will anyway remain same. So this is our final answer. So this is the complete answer. Now consider this problem. Here, a particle having charge q is fixed on vertical insulated wall at point A. Here is the point A and here is charge q which is fixed to the wall. Now it says a second particle B of mass m and charge q is suspended by a silk thread of length L from point P on the wall, that is L distance above A. So this is the point P from which on a silk thread another charge q is hanging, and this point is at a distance L from A. So both the length of the thread is L and distance AP is also L. Now it says calculate the angle made by the thread with the vertical when Q stays in equilibrium. So we release Q in equilibrium condition. So we have to find this angle theta right here. So I have drawn the diagram here to solve the problem, and I have drawn the free body diagram of the charge Q. So let's say this is the charge Q at point B. So it will experience a tension along the string but away from Q. This is the tension here. There will be electrostatic force of repulsion. This is that electrostatic force here, and mg. Now let's try to solve the problem. So to solve it, first we are using sine law. So we are applying sine law, but sine law for force. Sine law for force. So what does that mean? Now, if we consider the three sides also, the triangle, it is a enclosed triangle. So in that case, we can apply sine law for triangle also using the side length. And also we can apply the sine law or Lami's theorem using the three forces. If there are only three forces and all three are coplanar and the resultant is zero, means the system is in equilibrium, then we can apply sine law for the forces as well. So in this case, if we are writing applying sine law for force, so in that case the equation says, let's say we start with F, the force F. So F by sine of angle between the other two forces. Look here, this is the force F. So we have to consider this angle. If we write F by sine something, this, then at this term we have to write this angle. See here, this is theta, right? If this angle is theta and this is also vertical, if this is theta, then this angle will also be theta. So in that case, this remaining angle, I can say 180 minus theta. So I am writing F by sine 180 degree minus theta equals, now this is mg and we have to write this much angle now. Mg by sine of the other two angle between the other two forces. So the other two forces are tension and F. The angle between them is this much, which we can write as 180 minus alpha, because this angle is alpha here. So I can say the next term as mg by sine 180 degree minus alpha. For the third term, I need tension, tension here by sine of the angle between the other two forces. So the other two forces, angle between the other two forces is this much, which will also be equal to alpha plus theta. So this is alpha plus theta here, because from this diagram we can see this angle and this angle are all same because they are opposite angles. So I can say the angle between mg and F will be alpha plus theta, even though we won't be using this term, but still applying sine law we are writing the entire term. So this gives us sine alpha plus theta. We won't be needing this third term here. These two will suffice for us to solve the question. We will need some more equations as well. Now let's see another aspect of it. Look, this length is L, this side length is also L. So if I draw a perpendicular to the foot of the base, I can say this much will be L sine theta by 2. Look, because this angle will be theta by 2 and this angle will be 90-degree, right? So from a right angle triangle like this angle is L, this sorry side is L, this angle is theta by 2. So this side becomes L sine theta by 2. So the total base here, the length AB, I am writing this term here, we know it is A. So length AB we can write, that is 2 times, because half length we got L sine theta by 2. Total AB length will be 2L sine theta by 2. So if I write these two terms together, look, the equation looks this way. F becomes K Q naught by AB square, the side AB. We are applying Coulomb's law, K Q1 Q2 by R square. This much should be equals to mg by sine, sorry, here there is another term I am leaving, AB square into sine theta, AB square into sine theta, because the term here says F by sine 180 minus theta, which is equal to sine theta. So F is K Q naught by AB square by sine theta here. Now mg by sine alpha. This is the equation we are getting. Now how do we relate theta and alpha? Now we are applying sine law again, but for the triangle. See, this is the triangle here. So from for the triangle we can apply sine law. How does it look? Let's see. I can say this length right here is AB and this angle is theta. So I can write AB by sine of the opposite angle, which is sine theta, should be equals to any other side L. This side is L and this angle we have assumed to be alpha. So this much by sine alpha. Here alpha is not given, mind it. In the question they have not given us alpha. We have assumed the alpha term and finally we will try to eliminate alpha. That's what we are trying to do right now. This alpha term we will now try to eliminate. Then we will get theta in terms of Q, Q1, Q2 and mg and all those terms. So from here, from this equation, here we have applied sine law. So let me write it. Applying sine law again. But now it is not for force. This is for sides of triangle. We have applied sine law for the sides of triangle and we got AB by sine theta equals to L by sine alpha. But AB term, we have already written the term AB. AB is 2L sine theta by 2. So let's replace it. So AB term equals 2 times L sine theta by 2 by sine theta. Sine theta I am writing as 2 sine theta by 2 times cos theta by 2, because sin theta by 2 can cancel out now. This will be equal to L by sin alpha. Now see here again, this L term gets cancelled, the 2 term also get cancelled, sin theta by 2 and sin theta by 2 get cancelled, we get cos theta by 2 here and sin alpha here. So this equation gives us sin alpha equals to cos theta by 2. So we will use this equation in our original equation which was relating the two forces. Now let's apply these two equations, these equations here. So we'll try to solve it. Here we are getting K Q naught by AB square. The AB square terms gives us 2L sine theta by 2 whole square into sine theta equals mg by sine alpha. Again sine theta term we can write like this, 2kq by 4L square sine square theta by 2. Now sine theta I am opening again as a 2 sine theta by 2 times cos theta by 2, and this is equals to mg by sine alpha. But now only we got to know sine alpha equals to cos theta by 2. So this cos theta by 2 and sine alpha term cancels. So let's cancel them. This one and this one cancels. Look, here we have got sine square theta by 2 and sine theta by 2. So net sine cube theta by 2, I am taking them to this side, sine cube theta by 2. The sine cube theta by 2 term I am taking to the right side. So I am getting total sine cube theta by 2 equals, so the remaining terms are k q naught by 4L square and 2 becomes 8L square mg, right? Is there anything left? K q naught here, 4L square sine square theta by 2 into 2 becomes 8L square, and sine cube theta by 2 is here, cos theta by 2 is cancelled, and mg terms comes here. So from now, if I write theta, theta comes to be sine cube theta, so I can take cube root, so k q naught by 8L square mg, this much to the power 1 by 3, but this one's sine inverse will be applied and 2 will be multiplied, because here it is sine theta by 2, so at the end theta will become 2 times. For sine bringing to the right side we will get sine inverse, and this cube here on the right side will become cube root. So theta comes to be 2 sine inverse k q naught by 8L square mg whole to the power 1 by 3. So this comes to be the answer of this problem.